Deep learning, or deep neural networks, have achieved state-of-the-art performance on many problems in the recent years. Can one easily, without expert knowledge, train these deep neural networks on bioacoustic problems? Hello everyone, and thanks for joining in on this talk. My name is Emmanuel Dufourq. I'm a postdoc researcher at the African Institute for Mathematical Sciences and Stellenbosch University. And the title of this talk is Creating Pre-trained Neural Networks for Bioacoustic Monitoring. I will take you on a journey on how to, with little knowledge and without a PhD in machine learning, on how to use pre-trained neural networks, in other words, to reuse models that have already been made, and how these were applied to four acoustic classification problems. I'll break down the ideas into small chunks so that they're easy to understand and so that you can also apply this methodology. Neural networks are essentially made up of units represented by circles and weights represented as lines. Networks like this enable us to create classifier models that help differentiate between different things, for example, images of cats and dogs and audio of different bird calls. When building a network from scratch, the weights are randomly initialized numbers, for example 0.1 or minus 0.2. Given that the weights are initially random, this results in poor classifier performance. Therefore, we need some way of updating the weights so that the models can learn how to classify different things. Using mathematical optimization, we can update the weights such that the neural network's performance can be improved. Now think of an old AM/FM radio where you have to turn the dial to get the correct frequency for the radio station you want to listen to. For a moment, just pretend that a single weight in a neural network is like that dial on the radio. In other words, you have to change the weight so that you can get the correct output that you want. Now imagine that in order to get the correct radio station that you want to listen to, that you have to change 2 dials at the same time. Or even worse, that you have to change 100 dials at the same time. So now it becomes actually quite hard to get the correct radio station because you have all these dials to update at the same time. Neural networks are made up of a number of layers. It could be 3 layers, 5 layers, or 100 layers, but one has to actually decide on that number. And one has to also decide on a number of other things, such as the number of units in each layer and things like activation function and order of layers. So there's actually quite a lot of decisions that the user, from a modeling perspective of the network, has to decide before even executing any code. Deciding on all these choices is what makes designing neural networks quite hard. This becomes a little bit easy with time and practice, but can be a bit daunting for someone who doesn't have a lot of experience in this. Convolutional neural networks are the state-of-the-art for image classification problems. These networks contain convolutional layers, which help the network to learn useful visual features, which in turn enable good performance. This is the case because, loosely speaking, convolutional layers learn how to visually abstract. This is somewhat similar to how humans can abstract and recognize visual things. For example, we can recognize a human by the fact that we can see 2 eyes, a nose and a mouth, and the location of the nose with respect to the eyes and the location of the mouth with respect to the nose, and so on and so forth. So in other words, we can abstract all of these visual concepts and recognize people, cats and dogs, for example. And that's the same idea with the convolutional neural network. Layers towards the start of a network learn simple things like lines and blobs. And then the next layer uses the previous layer's information to learn even more complex things, such as more complex shapes, and so on and so forth, until ultimately this enables the network to learn very complex visual entities, such as a picture of a person or a picture of a car. A lot of work has been done in the field of computer vision to create deep neural networks that can achieve very high performance on image classification problems. I was curious to know if we can reuse these models that achieve such high performance and apply them to bioacoustic problems. Since we can represent sound through a spectrogram, which essentially resembles an image, then perhaps we can use these existing neural network models to bioacoustic problems, and if so, how would we go about this? In recent years, the idea of transfer learning and deep learning has received a lot of attention. Transfer learning is when we train a model to achieve good performance on some problem, say problem X, and then we reuse the same model, potentially adapting it in some way or another, and applying it to a similar problem, say problem Y, and we get good performance on that problem too. In other words, instead of training the model on problem Y, which might have very little data, we find a similar problem and we start there instead. Why is this important? Well, it turns out that to train good deep neural network models, we need a lot of data. And if we don't have a lot of data, then we can find a similar problem that has a lot of data and train our model there as a first step, and then transfer that model and adapt it to solve our problem that has very little data. Consider the problem of face identification. In other words, training a model to recognize images of people. Kind of how social media companies tag you and your friends when you upload images. If a convolutional neural network is used, then the layers in the network will learn useful visual facial features. Now consider the problem of facial emotion recognition. In other words, training a model to recognize whether a person is happy or sad in a picture. Now pretend that this dataset has very few images, and we know that deep neural networks perform better when we have a lot of data. What we can do is pre-train a convolutional neural network on the facial identification dataset and then reuse the model and adapt it to the facial emotion recognition challenge. In this example, I have described how transfer learning can be applied. Now it turns out that this approach is very useful when one has very small datasets. Now let's go back to the bioacoustic problems. These datasets are usually small or have highly imbalanced datasets in that you have very few examples of audio for the species that you're interested in. The immediate question is, can we use transfer learning to train good classifier models for bioacoustic problems? What would we pre-train our models on, and what would be the resulting performance on these bioacoustic problems? There are a number of ways of approaching this, and I will describe one way that worked well in my investigations. ImageNet is a dataset that contains millions of human-verified pictures that have been annotated into one of 1,000 classes. In other words, it is the 1,000 class image classification problem. Over the years, a number of researchers have built models on this dataset. More specifically, they have built convolutional neural network models that have achieved very good performance. If we wanted to use one of them for our transfer learning approach, which one should we select? Let's go back to the idea of neural network weights. Large models, in other words, models with a lot of layers and a lot of units, contain a lot of weights, sometimes millions of weights. It turns out that training these millions of weights on a small dataset can result in suboptimal performance. Keeping this in mind, and coming back to our model selection for transfer learning, I selected MobileNet v2, which achieves very good performance on the ImageNet dataset, but also has a reduced number of network weights in comparison to other models that have been applied to the ImageNet dataset. Now let's formally define this investigation. We would like to use the Mobile v2 neural network, which has been pre-trained on the ImageNet dataset, and we would like to fine-tune it to a bioacoustic dataset. MobileNet takes an input shape of 224 by 224 by 3. In other words, it expects an input to have a depth of 3 because the network was trained on color images in the ImageNet dataset. The depth of 3 is because color images have 3 channels, R, G, and B. Spectrograms, on the other hand, only have one color channel, or one channel. However, these are often visually represented using colors. So now that we have a mismatch between our spectrograms only having a depth of 1 and MobileNet v2 expecting a depth of 3, we need a way to solve this. So what we can do is repeat the spectrogram 3 times by stacking the layers on top of each other, and thus meeting MobileNet's depth requirement of 3. In terms of the width and the height, if we use the TensorFlow library to implement the neural network, it will actually resize the image to meet the 224 by 224 input. All the datasets were downsampled to 9,600 Hz. A number of audio segments of varying length from 2 to 5 seconds were extracted from each of the classes and input into the neural network. To generate the spectrograms, I used a window size of 1024, a hop size of 256, and 128 mil frequency bands. Thus the input on average was a 128 by 94 by 3 input picture. For this investigation, I used 4 acoustic datasets. The first was a sound classification dataset containing urban-related sounds. This dataset was selected so that I could benchmark the transfer learning approach against other studies in the literature and other neural network implementations. The remaining 3 were bioacoustic datasets. The first dataset is the Urban Sound 8K dataset. It contains 10 different classes and is available at this link. Here are some examples from each of the 10 classes. dataset formed part of an acoustic monitoring project to create neural network classifiers for the world's rarest primate species, the Hainan gibbon. This was formulated as a binary classification problem, and we wanted to know if an audio segment contained or did not contain a gibbon call. This dataset is publicly available at this link, and here are some examples from both classes.
My name is Amanda Hübner, and I'm from the University of Utah. The orangutan dataset was collected in collaboration with the Borneo Nature Foundation. In the Sabanga Forest of Central Kalimantan, Indonesia, we followed male orangutans for the duration of their activity period to record the long-distance vocalization they produce called the long call. We did this from August 2012 through December 2015 and have over 200 recordings of these long call events. Simultaneously, as we were doing these follows, we also used 3 automated recording units to record the forest 24/7 to pick up these long calls on these devices. We hope to be using the models trained on those high quality acoustic recordings from the follows to then apply it to these automated recording units to be able to find these long call events.
The fourth dataset was collected in Cape Town at the Ntaka Island Nature Reserve. I collected a number of audio segments containing calls from the Egyptian geese and a number of other species. I formulate this problem as a binary classification problem. The dataset was recorded using handheld recorders and contains very few audio examples. This dataset is actually a perfect challenge for the transfer learning approach, as we would like to know how well the approach would work given that this dataset contains very few recordings of the species of interest, in this case the Egyptian geese. This dataset has not yet been made publicly available, as I would like to collect some extra data before releasing it. Here are some examples from both classes. For the Urban Sound 8K dataset, the fine-tuned model obtained, on average across 10 executions, a classification accuracy of 82% on 1,747 audio examples. For the gibbon dataset, the fine-tuned model obtained, on average across 10 executions, a classification accuracy of 98%, and that was on 856 audio segments. For the orangutan dataset, the fine-tuned model obtained, on average, across 10 executions of the neural network, a classification accuracy of 98%, and that was on 719 audio segments, with the best model achieving 99% testing accuracy. For the Egyptian geese dataset, the fine-tuned model obtained, on 10 runs, an average accuracy of 96%, that was on 244 testing examples. These models contained 8,000 neural network weights, which is relatively small when compared to models containing millions of weights. I attempted to create the best possible model I could from scratch, which took a fair amount of experimentation, and on average those models achieved 8% less classification accuracy than the transfer learning approach. To conclude, the empirical findings presented reveal that transfer learning is a suitable approach for training deep learning models. One does not need as much of a strong foundation in machine learning when using this transfer learning approach as opposed to training neural network architectures from scratch. The approach is not flawless, and good performance will depend on correctly annotating the dataset to reflect variation in environmental noise. I hope this talk has been informative and that the bioacoustic community can benefit from studies such as this one. Thank you for listening to this talk, and feel free to reach out to me via email if you have any questions or comments.